presenting beneficial and harmful explanatory machine learning today. So this is a project, collaborative project between computational bioinformatics lab at Imperial and also the cognitive system group at the University of Bamberg. So let me just use laser pointer here. So there's some current challenges and issues within explainable AI research. To name a few, some of the core ideas and core concepts are not very well and not very formally defined. And also at the moment, many of the studies do not have support from empirical human trials. And also the studies exclusively focus on the beneficiality, the bright side of machine-generated explanations. So to target to some degree, target some of these issues, we made the following contributions. So we offered a definition that's operational to measure the explanatory effect of machine learning. And we use a framework based on what we call a cognitive window to explain the effects. And most importantly, we use human trials to support our framework and these definitions by the demonstration of both beneficial and harmful explanatory effect on human comprehension. So a key question is, how do we measure human comprehension operationally? This question was addressed by Schmid and Stephen Muggleton in their 2017 paper. And they defined human comprehension based on out-of-sample predictive accuracy after studying the training examples. And based on this definition, we refer to human learning that's machine-aided when they were provided both training examples and explanations. And we refer to self-human learning when they were only provided with training examples. A significant positive test result from a comprehensibility test would correspond to a beneficial explanatory effect. And contrarily, if the test result is significant but negative, that will indicate a harmful explanatory effect. So our cognitive window framework can be summarized into basically two bounds. So human learning becomes rather ineffective when the hypothesis space of the program class in which the program is in exceeds the hypothesis space that can be the size of the hypothesis space that can be searched by humans in large margin. So it wouldn't be effective for humans to search that many hypotheses. On the other hand, on the left-hand side, we have the complexity of the program which we aim to teach, ME, M being a machine learning algorithm, E being a set of training examples. And on the right-hand side, we have the complexity of a program that's learned from a sufficient and necessary set of background knowledge. So when this holds, the complexity of the program that we are aiming to teach is greater than the cognitive cost of what we call a program solution, then execution becomes inefficient, and therefore there is a lot of load on human working memory. In order to test this in a human trial, we designed an isomorphism to noughts and crosses, which is relatively popular and common. so the isomorphism aims to avoid the ceiling effect that we may encounter in the human trials while retaining same level of complexity. So using using nouns and crosses as an example, the easier category of questions will be you only need to fill in one mark as player X and you win. And the hardest type of questions will be you fill in one mark and you need to consider all the other positions that follow your move in order to win the game. And you need to span out all different combinations, all different alternatives to see which one is the optimal one. So in the original nouns and crosses, player X would need to, in order to win, the player X would need to fill in 3 pieces in a line, whereas for our newly designed game, the island game, the isomorphism, a player not only has to the player has 2 choices. One, either to occupy 3 cells on the same island. You see that blue has already taken this cell and this cell. So blue, in order to win, could take this cell. Or a player could get 3 of the same resource. For instance, orange here would have won if orange had taken this cell, because orange already has 2 of the castles here and only 1 is missing. So the icons are graphical representation of either a row, a column, or a diagonal in the original nouns and crosses game. Also, we changed the spatial layout to make it a little bit challenging to relate the island game to the original nouns and crosses game. So we consider 2 meta-interpreted learning frameworks for the machine learning side. So one is MyGo, which learns basically a minimax algorithm for winning and drawing nouns and crosses from sufficient and necessary background knowledge that includes a classifier for winning and also a classifier for valid moves. And MyGo does that from positive examples only. Additionally, we also have MyPlan, which is the extended version of MyGo. It uses an additional background knowledge and learns a smaller program with less inferential cost from both positive and negative examples. So the additional background knowledge can be illustrated here with this example. So imagine I fill X here down the corner. I'll create simultaneously 2 attacks. So one here, another one is open here. So this is what we consider a geometric feature and what we call a pair. So going back to the program learned by MyPlan, these 2 clauses specifically, which correspond to the example that I just shown, a winning move and optimal move not only should be a valid move, but also it should satisfy that X would open up 2 attacks and open up 2 pairs, while your opponent O do not have any of the attacks open, because otherwise your opponent could throw you in just 1 move. So in terms of the experimental setup, we use a rather conventional control and treatment setup, with the treatment being explanations. The explanations come in 2 partitions. One part is the English translation of the learned theory, and the other part is basically visualization of the game state to ground the textual explanation. And the visualizations are offered in contrastive sequences. Sorry, there's a typo there. As illustrated by this diagram, you can clearly see that there is the sign of a harmful effect, as indicated by the reduction in performance after participants have been presented with explanations. And also, we see that there is an improvement of performance after receiving explanations, which will correspond to a beneficial effect. And at the same time, we see that this group do not have any noticeable, observable change in performance. To sum up, we observe from all the experimental results that there is a bound, generally a bound on the program side learnable by human subjects. And also heuristics do play a very important role in alleviating the pressure on working memory load, therefore improving short-term comprehension. And these support for our cognitive window framework. So we have been planning some future works, which includes looking at the curriculum order and how that affects human comprehension in this teaching setup. And also in the future, we like to involve human feedback more into the loop by taking into account how well people adjust to machine offer corrections and let machine learning happen during the teaching procedure. Yeah, thank you very much. That'll be everything. And if you're interested, please come to poster 7 in the future poster session. Thank you.